Welcome to this series of introductory videos from SolidCAM. This video's topic is 2D iMachining. We covered the basics of 2D iMachining in a previous video where we talked about the definition of your machine and your material for the purposes of iMachining. Here we're going to use that functionality to actually generate a 2D iMachining toolpath. Let's take a look at how you would do that. So to get to the 2D iMachining toolpath, you can either go to the SolidCAM operations. You'll find 2D iMachining in the operation menu there. If you go to SolidCAM 2.5D, you can find 2D iMachining there, or you can just right-click on Setup, Add Milling Operation, and you can find it at the top of the list. Now, I've already created a couple ones here. We can review how they were done. A lot of this is going to be similar to what we saw in the pocket operation toolpath of this introductory series, because this is essentially a optimized pocketing toolpath. To add a 2D iMachining, you need to add those definitions. So you can either do that right at the beginning when you open up your CAM part. So again, a lot of stuff in this window is covered in the starting new CAM part video, so you can take a look at that as well. I've already got my post, got my stock and my target, coordinate system. We'll go down here to the iMachining database section. This is where we will apply those database entries that we did in the basics of iMachining video. So here's my per VMID. I selected it from the menu. Here's my 6061. I selected it from the menu there. Now, even though in the previous video, we did it in more of a global setting, we went to Tools, SolidCAM, iMachining Database. Here, we can actually do it inside the part file. We can just click on iMachining Database. We'll actually add our values here as well. And this is still the same global library. So if you create a machine database entry or a material database entry within a CAM part, it is still a global entry. So anything you define here, you can use in other places. And you can add those database entries either right from the beginning when you define your CAM part, or as you go along and you want to add an iMachining toolpath, you can always go back and add that as well. So let's take a look at 2D iMachining. Let's just open up this first example here. And there are actually 4 modes that you can use in the iMachining geometry, feature recognition modes. This one is a good representation of the classical mode or the chains without feature recognition. So this essentially is a iMachining version of a pocketing operation. Each one of these modes will help you to do that type of pocketing operation, but this particular mode is more like a pocket than anything else. You choose your chain and you choose your upper level and your lower level. So to see how to do that sort of functionality, I would refer you to the pocket operation video, but here we can just kind of review it real quick. So I actually went to New Geometry. So the interface looks the same as a pocketing. I chose constant Z, and I chose that upper pocket there. So same sort of functionality we have with pocket. I'm just going to use the one that I have there, you see there. I mentioned in the getting started with milling CAM part that you don't necessarily have to add your stock and your target. So if you don't add your stock and your target, but you want to use iMachining, you can use this option here. If you do have your stock and target defined, then that opens up these guys here. You can actually use these because these will use stock recognition. But again, let's start with this basic one here. So even though we still have the ability to do stock recognition, tangent protection, and collision protection against the fixture, we're not actually using that here because we're not using a recognition mode. So all of this is based only on the geometry and my entry. If we go to Tool, I've selected my Tool 3, which is a 1/4" tool. And because this is iMachining, it's going to calculate the fees and speeds for me. That's because now that it knows the end mill that's being used on the machine to mill this material, it has all 3 bits of information to calculate those fees and speeds for me. So in the data section of an iMachining toolpath, you'll see that we have the feed and speed locked out. Those are locked out because those are being calculated for us by iMachining. But at any point, if I want to turn off the automation, I can always click the wizard to off, and then I have control over the fees and speeds. But the purpose of iMachining is to get that automation, to get that optimization. So I'll leave that turned on for now. Under levels, very similar to what we saw with the pocketing operation. I can tell it to use my upper level and my lower level. One quick note is if you do have your stock defined and your target defined, you can use those to define the upper level of your toolpath. So that's why I'm using my top of stock, and it's reading the top of my stock that I have there. For my pocket depth, like we said, again, just like in a pocketing operation, I've clicked on the lower face of the part, and I've told it to go an additional 30 thou from there. So up until this point, this is pretty much like a pocketing operation, because essentially it is a pocketing operation, just using the iMachining algorithm to control the fees and speeds, and in the next window to control the step down and the step over. So In the technology wizard section, this section is actually unique to iMachining because what you're doing here is you're controlling how aggressive that iMachining calculation will be. So we'll look at the step down first. So with the automatic setting turned on, it's actually looking at the flute length of my tool. So if I click on that, I can see that I have a flute length of 1 inch, but this pocket is 1 inch and a bit. So if the pocket height was less than the flute length of the tool, we would get a full depth of cut. We would have the tool going right down to the bottom of the pocket and milling out the pocket. And we can achieve that because of our iMachining algorithm is controlling the material engagement. It's taking a look at things like cutting angle. It's using that material and machine information to see the limits of the machine and the material to determine how best to do that full depth of cut. But it will use the full flute length as the depth of cut for any pocket that you generate. So in this case, because it actually would have to do it in 2 depths, it's equalizing the pressure on the tool by doing it 2 depths of an equal step down of this case 0.65, which generates an ACP of 166. ACP is axial cutting points, pretty much meaning that the number of flutes on this tool that I've defined, as they revolve, there is at least 1 point of contact with each revolution. So it's a very efficient use of the tool. It's not the most efficient. The yellow indicates that it's not the most. There's probably something I can do here, maybe switch to a different diameter tool, a different flute length. I'm trying to use as much of the tool as possible. I'm trying to optimize the use of the tool. So that 0.66 indicates that there's at least 66% of the flute that's still in contact with the material with each revolution. So there's probably a point of contact that's missing. I could probably do a different tool. It's not wrong, it's just inefficient. So like I said, if I chose maybe something different, I would get a red color indicating a lower efficiency or a green color indicating a greater efficiency. So we can take a look at that here. If I change from automatic to user defined, I actually can define the number of steps. So let's say I tell it to do it in 5 steps. So if I do this in 5 steps of 260, I'm getting that red color because I'm getting an ACP of 0.66. So an inefficient use of the tool. I don't need to take it in this shallow of a cut, but maybe there's a reason why I need to do that. So I'll switch it to user defined and use number 5 steps. If I do step down, let's put a step down of 100 thou. That is also an inefficient use. And you can tell because it knows to do it in 12 steps of 100 thou with that final step of exactly 100 thou. And that's giving me an ACP of 0.25. So I can take control over the automatic nature of this toolpath, but a lot of the times, if you're trying to get that optimization, iMachining is already giving it to you with automatic. In terms of the feeds and speeds, they're represented here as well. And you can see that I have this set to level 8. I'm getting this to go as fast and as hard as possible. But if I slide this back and forth, you'll see that those feeds and speeds increase or decrease as I slide this back and forth. That's because the machining level is a level of aggressiveness. So even though it's calculating feeds and speeds for me, I can tell it how aggressive to make that calculation. Another thing you'll see here, very visual representation, is the flute, the chip thickness is increasing or decreasing as well. And again, that is to do with how iMachining works. iMachining is looking to maintain a chip load. It does that by maintaining a chip thickness. So to maintain that chip thickness, it regulates the feed and speed and the cutting angle throughout the toolpath to maintain that chip load. The main focus of iMachining, and that's basically why we're controlling the feeds and speeds so controlled here. If you go to modify cutting conditions, there's some additional parameters you can use to further dial in this toolpath. And the purpose here, again, is to get this to be optimized. So for instance, if you know that you can only go to a certain chip thickness, you can plug that value in here. If you know that your holder can't handle the maximum RPM of your machine, you can check this box here and change the value there. All you're really doing here is really dialing it in to further represent the exact combination of machine, material, and end mill that you're using. One last thing, turbo mode. Turbo mode actually doubles that chip thickness, or effectively doubles that chip thickness. And because the chip thickness is responsible for how aggressive this is, once you turn on turbo mode, you're effectively looking at levels 9 to 16. So level 8 turbo is as fast and aggressive as this thing is going to get. Under technology, this is an automated toolpath. So it'll take over and control the cutting angles and the step over for you. But again, anytime you want to take control, turn off the wizard, and now you have control. But if you have it full on with the wizard and full automation, what you're really doing here is just telling it how much material you want to leave on the walls and the floor. In this case, I'll just leave it with those defaults. And then lastly, in the link section, iMachining by default will do a helical entry into cavities and a side entry whenever there's an open edge or a fully open pocket. So those are the two options for the entry of an iMachining, but with respect to the helical, you can put in proper ramping angle according to your catalog data for your tool if you need to. And if it's a non-sensor cutting tool and you need to give a step down to that helix, turn that off, and you can see that you can put a step down in there as well. If you have a drilling operation before you do this 2D iMachining, you can use that drilled hole as a pilot hole. All you got to do is just tell it to recognize the pre-drill operation, and then it'll select that hole as an entry point. So instead of doing a helical entry, it'll plunge down that pilot hole. So since I've already calculated this, let's take a look at the wireframe of the toolpath. So you'll notice first thing, there's one entry, one exit. This rapid movement here is just to go down to that second depth of cut. If we take a look at it kind of a little closer, you can see there's our helical entry to the first depth of cut. If we take a look at this from the point of view of the tool, we're doing what's called a morphing spiral. So from that entry helix, we're morphing out. You can see that it's a non-constant step over, again, because we're trying to control that material engagement. We're regulating the step over in addition to the cutting angle, the feed, the speed to maintain that chip load. Those red lines represent rapids. Those rapids are skimming across the top of the material. We know we already removed the material. There's no need to exit completely out of the pocket just to avoid any material. So we're reducing the cycle time just by doing that. Once we achieve the morphing spiral to a point, we'll see that we have to get into these corners. So you can see that it actually is doing what's called the D-slot tricoidal. It actually works its way into that corner, never doing a 90-degree turn, never going to hear a squeal in your iMachining because it's always maintaining that material engagement. So that was what we call the classic mode, or chains without recognition. But now let's see how this works when there is some recognition. Okay, so you can already see a few differences. One, as soon as I choose the recognition by chains, and I've got my chain represented as the top edge of that cavity, you can see there's a blue preview there. And that's because it's recognizing from the updated stock. As soon as I tell it which tool I'd like to use, it gives me this preview. It recognizes that that center pocket has already been milled out by the previous iMachining toolpath, so it recognizes that bit of stock. And if I go into my levels, it goes right to the top of the stock. But in this particular recognition mode, it only recognizes from the chain going upwards. It needs to know the depth that I want to go to. So if I take a look at my levels, I actually had to select the top of these pockets here. But if I select even further down, it'll further recognize the stock and make sure that I don't gouge those tabs or gouge that center island. But I'm just going to switch that back to here because I want to utilize as much as possible this area here. I want to mill that out. So it's going to mill all that out for me from the top of the stock down to the face that I've given it. The preview also shows me what else is going to happen here. In this case, this tool won't fit in those corners. If I just do a top view of this, this is a 1-inch tool, and those corner rads are much lower. So as soon as I tell it I want to go to this distance, it'll show me that I'm going to be leaving material behind there, which I will be able to take care of in another toolpath, because this being a recognition toolpath, it's always looking at the updated stock. So this will actually become stock for a follow-up toolpath. Again, this is at level 8 turbo. Using its own particular parameters, it's recognizing that if I did this in one depth of cut with this 1-inch tool, it's possible, but it's giving me an ACP of 0.57. So maybe the 1-inch tool, even though it can hog out a lot of material quickly, it's probably not the most efficient use of this particular tool. But I'll go with it because it fits what I'm trying to do here. And let's look at that wireframe as well. So because it recognized that that material was missing from the center, it did a side entry, and it morphs its way out from there, and it works its way into those corners. This one, we're going to use the next recognition mode, and that is using faces. Now, this one is a very powerful one. This utilizes the same sort of smart face technology we saw in the pocket operation video. The geometry is the face itself. I chose that bottom face right there, and from there it recognized the outermost chain, the innermost chain. That blue haze there, that is the preview showing me again that this same tool can't go in that corner. It's going to mill as much as it can around those walls. And I also, again, have the stock recognition and the target protection there as well. So it's generating a toolpath based all on the geometry, even the levels themselves. because I've chosen that face, it knows that that's the lower level of my face as well by default, and it made it associative. You can see that it projected upwards to the top of the stock, but for this operation, since I've already milled down to this face, it knows to start this toolpath at that face. So the preview shows me that as well. Same tool, level 8 turbo, and I'm leaving some material on the walls and the floor here as well. If we take a look at that one, it recognized that that's really the only area I want to work in, but that's still a type of cavity. So it still has the helical entry, and because it can't really achieve a morphing spiral in this exact area, we're getting more of that separation channel. We're getting it to work its way through these little bottlenecks here, still doing iMachining. It's still doing that kind of deslide movement to make sure it never buries the tool, even if it really just has to do this kind of a slot area. So now let's see the smart face with a little more sophistication here. If we take a look at the faces selected here, it's the same face, but the stock recognition is recognizing that I'm using actually a second tool in my multi-tool window, and that is using a 1/2-inch tool. And from there, it's giving me this representation here of the material that it notices that the previous tool left behind, and that is those corners I was talking about. So in the same operation, I've given it the second tool. The tool is a smaller diameter, so it can do more things than the previous tool did. And it actually is recognizing even the walls themselves. So it's actually going to just machine what it can from there. So if we take a look at that toolpath, it only focuses on just those corners there. It's still doing a type of iMachining. It's still basically working its way into the corner, never burying the tool, but it's only working on what was left behind by the previous toolpath. Okay, another type of recognition is the fact that I'm using the same tool, but now on this face, and again, it recognizes that that's pretty much the only material left on that particular face, but it also is feathering out from there as well. So it extends from the chain. So if you remember from the pocket operation video, when we did Smart Face, it recognized the walls and the open edges, but from that open edge, it extends outwards to machine as much of the material as it can. And that is the leftover rad from this face here. So at this level, it has just a little bit of material that it needs to remove. It recognized that for me, and we'll see that again, it works only on the corners. And then the last type of recognition, because of the use of the stock and target, it actually is easy to do the perimeter, the outside perimeter of the part. Let's take a look at that. I'm using my 1-inch tool, and I'm using the outside feature recognition, and this doesn't require any geometry because the geometry is already there. It's the stock and target definition. So from the stock definition, from the outside of the stock, it works its way inwards to the inside to find the outermost edge of the target. So that's actually just between the outermost edge of the stock, outermost edge of the target. It recognizes all that material. It recognizes it as open to the air, so it'll do a side entry. All it's really asking me for in terms of parameters is how far down in levels to go. So again, this is one where you can actually select the levels. But it still also has recognition. So if there was some sort of flat here, or if I had my fixture holding this in place, it would still checking against the fixture for me. I can still get some collision detection going on in here. And the way that toolpath looks, again, side entry, and it's morphing its way around as well. As soon as it cuts off those corners, it'll just do one continuous move around there. So you'll notice that these are out of order. I probably want all my tool 2s to be together. So what I'll do is I'll just drag this guy up. So now I have my tool 2s all in order, but it wants to be recalculated, and everything after it wants to be recalculated as well. And that's simply because these are stock recognition toolpaths. So as soon as I affect any kind of change to my toolpaths, they will recognize the stock needs to be updated, and they will want to be recalculated themselves. Another thing to note is if we go into this toolpath here, this one's a good example. We are using the multi-tool function. So we actually have 2 tools selected in the same window. So that second tool is basically doing a semi-roughing operation. It's looking at just the corners for me. But if I also wanted that tool to do the wall and the floor, all I have to do is check these boxes, and that turns this into just a roughing operation. From just a roughing operation to now a finishing operation. It should give me the ability to do some finishing as well. So if I double click on tool 1, it brings up some of the finishing operation parameters as well. So I can turn this into a finishing operation in addition to a roughing operation. And that's using the multi-tool option. So basically, 2D iMachining is an optimized version of the pocketing operation. It allows you to control the material engagement a lot more, so you can utilize your tools a lot longer, basically increasing your tool life, reducing the tool wear. And a lot of automation there based off the stock and target definition as well. So it kind of automates some of the geometry selections as well. Gouge checking and such can really help with the programming of your part. Any questions on this or anything else from SolidCAM, just give us a call at 1-866-975-1115, extension 2. And you can stay tuned for the rest of the videos in this introductory series. Thanks for watching.